look at the lecture here. So this is a continuation of 2.8, which is about linear approximation. Let's remind ourselves what we learned. So fx, you want to approximate the fx using a nearby point A. Okay. Well, you may want to say fx is almost the same as fa, right? Which is not bad. Which is, sometimes it's an okay approximation. But you can certainly do better using the linear approximation by using the tangent line at A to approximate my function fx. Okay. So with that, you would have fa plus f prime A times x minus a. Okay. So this is the main formula we learned. And let me just repeat what I said. So you could say, oh, this is almost the same as fa. And this is an okay approximation, but not as good as this one. I also mentioned that there are better and better approximations if you use, instead of linear function, you use quadratic function. And you get a better approximation. Let me just tell you the result, and just for comparison, so you will know there are these other approximations. This is not required for this course, but it's good to know. So the quadratic approximation will look like something like this. This part so far is a linear. And then you add a quadratic term. That would be f double prime A over 2 times x minus a squared. Okay? I mean, basically what this says is that if you look at all the quadratic polynomials that approximate the fx, this is the best one. And you can do degree 3. So you can have a formula like fa, f prime, x minus a, f double prime times x minus a squared, plus a degree 3 term, which will be f triple prime a divided by 6, which is actually equal to 3 factorial. By the way, 2 is 2 factorial. And this here you can say divided by 1 factorial, which is 1. Okay. So 3 factorial times x minus a to the third. All right, now you see a pattern, don't you? And you can imagine this could go on to any degree. And as you increase the number of terms here, the approximation becomes better and better. So you can keep on going. And as n goes to infinity, the number of terms, n is the highest degree term here, you get something called a Taylor expansion, which again, you don't have to worry about it in this course. Those who take calculus 2 will certainly learn that. Taylor series, Taylor expansion. Okay. But now, again, we're going to focus on just a linear approximation. Let me also rewrite this formula in a different language. I mean, it's still in English, but it's different notations. I want to do that because if you read our book, our textbook, or some other book, you will see that. So another notation for that, another way to put this linear approximation is that before you use A to be the starting point, X is the point you want to focus on. So instead of A and X, now you're going to have x and x plus delta x. That is a new notation. All right? It's really just a notation. So the picture is exactly the same as before. Before it was a and x. We can use a different color for before. Before we use letter A here and letter x here. Okay? And now we're going to use letter x for the starting point, and then this here we don't want to use x again. Instead, you use x plus delta x. X plus delta x. Why you want to use this notation? Because when you have a picture like this, delta x is exactly what? How much it changes, yes. And this is often, people often use delta x to denote the changes. So that can be useful. And you have still the same kind of picture as before. Changing line at A, and then you basically use this. You want to compute the value at this point, you use that point to approximate. So this is exactly the same before. Since previously we used the letter P, Q, right? P, Q, R. Basically we use R to approximate Q. Well, with that notation, what will this formula become then? This was fx before, and now becomes what? F at x plus delta x, right? So the formula would be fx plus delta x. All right. That is approximately equal to, well, previously it was fa. And now we're going to write what? Fx. Okay. So we're going to write fx plus what? Before it was f prime a, and now we're going to have f prime x. Okay. And then what are we going to have over here? Okay, so you said it's x, because it's x minus a before. So now we're going to have x plus delta x minus x. But what is that? Is simply a delta x. Okay? So we can simply put delta x here. So this is exactly the same formula as this is written in a different notation. So you can put another box. Make sure that you don't forget that. Remember last time we did two examples. Example 1, compute an approximate value for square root of 101. Right? Example 2, estimate the amount of time you need to get from A to B, right? Using different speed. Okay? Let's do a few more examples. Let me do a harder example first, and then I will give you some time to do some exercise here. So I'm going to erase all the formulas and expect you all remember those. Find estimating the value of so you want degree? Well, when you see that, I think perhaps your immediate reaction is that this should be close to what sine of what degree? 30 degrees. So 31 is close to 30, so you get the right intuition. And what is the sine of 30 degree? That's 1/2. You just have to know it. And then not everyone will remember that, but you do have to know that. If you don't feel comfortable with that, write that on your index card. Okay? So sine 30 degrees is 1/2. Now you may want to say this is almost the same as 1/2. Okay? That is an okay estimate, but that can be considered as a zeros approximation, right? Rather than linear approximation. Remember we talked about linear approximation, quadratic, and degree 3, and so on. So before linear approximation, there's like a zeros order approximation. So you can say it's almost the same as 1/2, but we're trying to do better. We're trying to do a linear approximation for that. So just like before, we can let fx to be a function that we're going to apply. What is fx going to be? Sine x. So that is more or less obvious. X is sine x. Okay, so now we're going to decide which notation we're going to use. Are we going to use the old bond or the new one? Either one is fine. You have a preference? The old one. Okay, let's use the old one. With that, we need to decide what is a equal to and what is x equal to. What would you like a to be? Yeah, 30 degrees. A is a nearby point that is computationally friendly. So a is equal to 30 degrees. Okay? And then x is the value we're working on, 31 degrees. Okay? Remember the formula, we need to compute f prime a, and then we need to compute x minus a. Okay? So fa is equal to sine 30 degrees. And what is sine 30 degrees? As I just told you, it is 1/2. What is f prime a equal to? 0. Are you sure it's 0? Okay, what is the derivative of sine? Yeah, f prime x is cosine x. Therefore, f prime a is just equal to cosine x when x equals what? 30 degrees. This is a very handy notation. So you just write the function with cosine x, and then draw a straight vertical line and put x equals 30. It means plug in x equals to 30. What is that equal to? Well, that's cosine 30 degrees. Now, did you say this is equal to 0? Or?
Square root of 3 over 2.
Yeah, it's a square root of 3 over 2. That's cosine 30 degrees. You just have to know it. Okay? I mean, you could have used the fact that sine square plus cosine square equals 1 to determine it, and just worked out the algebra. So this is square root of 3 over 2. All right? What about x minus a? I feel like I should not write too low. It's okay with you, but you want to on the back. So I'm going to try it here. What is x minus a equal to? 1. 1. Let me put 1 degree here. It's 1. Okay? So are we going to just throw away everything into the formula and work this out? Okay, let's try it. So sine 31 degrees, which is our fx. Let me actually write the formula. I'm just writing the formula here so you don't. Fa plus a x minus a. What are we going to get? Fa is equal to 1/2. F prime a is square root of 3 over 2. And what's x minus a? 1, right? What are we going to get? We just get square root of 3 plus 1 over 2. Is that the answer we get? Don't copy it yet.
No.
What's the problem? Is this right?
No, that's going to put it at something like 1.3.
Yeah, so as you noted, square root of 3 is roughly a 1.732. Plus a 1 is 2.7 something. Divided by 2 is bigger than 1, right? And that's not possible. We know that sine can never be bigger than 1, right? So what's the problem here?
It's not 1. Was it 1 over?
Yeah, the 1 degree is not really It's not really 1 here. You have to rewrite the degree as radian. Okay? Why is that? It really goes back to when we derive the derivative, sine derivative equals cosine. When we did that, we really rely on the fact that we're using radian instead of degree. I don't know if you remember that. We actually drew the picture of sine x. It goes up and down like this. And we kind of convinced that I think one of you drew a picture here. First it was very vertical, then we decided it should be more flat. The picture is the tangent line at origin is roughly something like this, which has slope 1. Okay, in order for 1 to happen, we really use the fact that the height is 1, and here, from here to here is pi over 2, and from here to here is pi. And that's all in radian. It's not in degree. I mean, if you use degree, the number will be very different. Okay, the scale will be different. If you call this 360, then this will be way over there. The picture will be much more flat, and the derivative will be smaller, right? Okay. So we do need to translate that to radian. What is 1 degree equal to in terms of radian? So to go from degree to radian, you times pi divided by 180. Okay. If you don't remember it, think about x degree times that, and if it's 180 degree, they cancel, gives you pi, so that's correct. 180 degree equals to pi. And that means instead of 1 here, so I'm going to have to erase this. That part is not correct. Instead of 1 here, I should have pi over 180 here, right? And that will give you my final answer, which is pretty much just this one. You can rewrite this as 1 fraction. So those two together is 360, and then that's 180 plus square root of 3 pi. You can leave the answer like this, or if you're in the homework, you can use calculator and then determine the approximate answer. But in the quiz, you can definitely leave the answer just like this. All right, maybe that's enough examples. Let me give you some exercises that you can practice here. Questions? So, one, of 1003, and let's do another one. Exercise 2. Compute. Degrees. Why don't you just do those two? Again, people are welcome to discuss each other. I think this is okay, but so we can turn off the video.